Hey guys, so we decided to do number 8 on the test, which says, suppose that the position function of a particle moving on a coordinate line is given by s of t equals 2t to the third power minus 21t squared plus 60t plus 3. Its position graph is given below. So they were kind enough to give us both the position function and the graph. With this information, we can solve this two ways. One way is to find the first derivative of the position function, and the other way is to look at the graph, find the critical points, and see where it's increasing and decreasing. So now I'm going to show you the first way. So the position function says s of t is equal to 2t cubed minus 21t squared plus 60t plus 3. So the velocity function, which is the same as the first derivative, is equal to 6t squared minus 42t plus 60. So with this little piece of information right here, since it's t squared, we know that it's a parabola, and since 6 is positive, we know that the parabola is positive and it's going to be upwards. So the only choice that looks like this is B. And just to make sure that B is the correct answer, just plug in x values into the first derivative that are within this range. So that would be from 0 to 6. And just to make sure that B is the correct choice. So now we're done with the first method.
So now we're going to do the second way of answering this problem. What we want to do is look at the tangent slopes of different points on the position graph to determine the velocity graph. First of all, I looked at the spots where the tangent line was equal to 0. Looking at these points shows us where the graph passes through 0 on the velocity graph. So, going back to the position graph, we can easily see that at 2, there is a horizontal tangent, which means the tangent slope equals 0. And again, there is a horizontal tangent at 5. Now, knowing this, we can plot them on the velocity graph. By looking at our options, only B shows that at 2, the graph passes through 0, and again at 5, it passes through 0. But to make sure that this is correct, we can look at other tangent slopes on the position graph and figure that out through the velocity graph.
Okay, now that we know that the critical points are at 2 and 5, I'll draw the tangent line, which is horizontal, right here for you. I'm also going to draw a dashed line in order to help us understand the shape of the function that we're going to draw, or which is already drawn, which is B. It's not exactly a line, but this is the general idea for the shape of the graph. So, in order to get for a greater concept, we're going to use more tangent lines for the position function graph. So I'm going to draw one here, here, along the whole entire graph. And looking at the first tangent line I drew, we can see that it starts out very positive, as it does in the correct answer B, right here. And the second tangent line right here is less positive, which means that it is decreasing. So it's starting out very positive right here, and it is decreasing. And it's decreasing, excuse me, all the way until it gets to the critical point 2. Right here, as we can tell from this graph also. Now, after the critical point 2, as we progress through the x points and we look at the tangent lines, it starts decreasing even more. And then it starts increasing again as the x values approaches 5, or the second critical point, which we have right here. And it is 0 on the velocity, or first derivative function. Now the last two tangent lines I drew shows that it is increasing significantly. Now we know, after we drew this entire function, that it turned out to be a parabola, and these are the two great methods we could use to solve this problem.